What do detecting a single photon, a cell dividing, and a machine part passing a stress test all have in common? At first glance, nothing. But mathematically, they are the same. Each situation has a simple structure. You repeat the same trial many times. Each trial has only two possible outcomes: yes or no. We encode this with numbers: 0 for failure, 1 for success. This is called a Bernoulli trial. A single Bernoulli trial is very simple. It only tells us whether something happened or not. But the real power comes when we repeat the same trial many times under identical conditions. Now, we start counting. Out of many identical trials, how many successes do we see? How many photons were detected? How many cells divided? And how many components passed inspection? Notice what we are doing here. We are no longer interested in the exact order of successes and failures. We only care about the total count. This counting problem leads to the binomial distribution. This distribution describes the number of successes in a fixed number of independent trials when each trial has the same probability of success. There are in general three ingredients: a fixed number of trials, binary outcomes, and a constant probability of success. If these conditions are met, the number of successes follows a binomial distribution. This already tells us something important. We are not modeling how success happens. We are only modeling how often it happens. All microscopic details are ignored. Only the final count matters. That is why the binomial model is so general. Now let us answer the main probability question. What is the probability of getting exactly k successes out of n trials? Think of it in two parts. First, pick which k trials are the successes. There are many possible choices. The number of choices is n choose k. This number is called the binomial coefficient. It counts how many different patterns lead to exactly k successes. Each of these patterns is equally likely. That is a crucial point. Because the trials are independent and have the same success probability, every specific sequence with k successes has the same probability. Second, for one particular pattern, the probability is simple. Each success contributes a factor p, and each failure contributes a factor 1 minus p. So we get p to the power of k times 1 minus p to the power of n minus k. Multiply both parts, and you get the binomial formula. Now here is why this formula is so useful. It gives us the full distribution, not just the most likely outcome, but all possible outcomes and their probabilities. The expected number of successes is simple. It is n times p. If you repeat the experiment many times, the average count will settle around np. This is a direct consequence of adding up many identical Bernoulli trials. The variance is also simple. It is np times 1 minus p. This tells us how much the count fluctuates around its average. Visually, the binomial distribution is discrete. Each possible number of successes, 0, 1, 2, and so on, has its own probability. You can imagine this as a set of bars. Each bar represents one possible count. The height of the bar is the probability. When the number of trials is small, the distribution looks granular. As the number of trials increases, the shape becomes smoother, and the bars start to form a familiar curve. This structure appears everywhere. In biology, it models how many cells divide out of a population. In finance, it models how many defaults occur in a credit portfolio. Each loan either defaults or survives. 0 or 1. Count the number of defaults and you are counting successes in a binomial experiment. This makes the binomial distribution very important in risk modeling. It allows us to reason about averages, about uncertainty, and about extreme outcomes. It is also the foundation of many simulations. In Monte Carlo models, we repeatedly draw binomial outcomes to generate possible future scenarios. So whenever you are counting how often something happens in repeated yes or no experiments, you should think of the binomial distribution. In the next video, we will move beyond counting bars. We will switch from discrete outcomes to smooth curves and introduce continuous distributions, starting with the normal distribution. I will see you there.